Good morning, everybody. Today we're going to start with proving triangles similar. Before we get started, I just want to review some of the basic stuff we've already been over. Um, Sorry, there go my yawns. The basic stuff we've already been over with the similar figures. The first couple questions are just uh, true, false, kind of. Or actually, these are those always, sometimes, or never. Oops, pen on. Always, sometimes, or never. True. Type of statement. So pause the video before it really gets started, and I would try some of these problems. Make sure you guys can get them right. These are just similar figures, and see how you do on the always, sometimes, or never. Okay, so hopefully you pause the video and tried some of these statements and 8 and 10. So for number one, two congruent triangles are similar. That's going to be true. Or I'm sorry, always. I should say that's going to be always true. And if they're congruent, they would be technically considered similar with a ratio of 1 to 1, where they're equal to each other. So yes, that would work. Two squares are similar. This is always. Because all the angles in a square are automatically 90, you already have that in common. And then because all the sides are congruent, like in one square, all the sides could be, let's say, 4, and in the other one, all the sides could be, let's say, 7. Therefore, all the ratios would be like 4 over 7, 4 over 7. So it would work out that they were always similar. A triangle is, excuse me, a triangle is similar to a quadrilateral. That's never going to be true. Obviously, they have to have the same number of sides. Number four, two isosceles triangles are similar. That's going to be sometimes. It doesn't always have to be true, but it is possible. Two rectangles are similar. That's also just going to be sometimes. Although the rectangle, like the square, has the four right angles, the sides don't necessarily have to be proportional. I'm just going to sketch a quick one down here. So if this was my rectangle, and like this was 2 and this is 5, excuse me, my other rectangle, still having the four right angles, like this could be 3 and this could be 7. So they don't necessarily have to be proportional, and therefore they're not similar. So we're going to go with sometimes on that. Again, it could work, but it doesn't have to work. For the two obtuse triangles being similar, that's another sometimes. Oops. That's another sometimes. Excuse me. And with the two equilateral triangles, that is also going to be always, just like the square. And the reason that's going to be always is because, again, just like the square, if it's equilateral, the one thing you guys should remember at this point is that all the angles are 60. It's also equal angular. So therefore, if it's equilateral, that means, like, if this side is 3, this side is 5, all the sides are equal. So all the ratios would be 3 to 5, and it would work out. All right. For numbers 8 and 9, those where we have to actually use the proportions to find a missing value, etc. So let me just erase this so I won't have any overlapping here. And let's start. So for number 8, the way you would line up the sides, I would basically just, look at what angles it's in between. Sorry. So these two would be the ones that correspond. Again, you could put both of them from one quadrilateral together, or you can go from one to the other. It's up to you. And then the other one would be the 8. Again, I would want the 5 and the 8 to be on the same level because they're from the same shape. And then on the bottom, it would be my x plus 1. Cross multiply. I'm not going to go through all of the steps here just because of lack of space. But 5x plus 5 equals 8x minus 8 is what you should end up with. You end up with 13. Sorry, equals 3x divided by 3. Boyfriend just sprayed some ridiculous air freshener. It's got me choking. 4 and 1/3 would be the answer, or 4.3. It's ridiculous how much he's read. All right, number 9. For number 9, again, they're similar. The way you should be picking which sides to line up will, this one is basically just visual, but it's this side here, like right next to the right angle, or, you can a leg for the right triangle. So these are going to be the two that go together. So again, I can do 4 to 6 or 6 to 4, whichever one I chose. And then because I put 4 first up top for this one, I'm going to put my x plus 7. And then my 12 minus x. And then again, I'll cross multiply to solve. I'm just going to skip steps here. 6x plus 42 equals 48 minus 4x. I'll end up with 10x equals 9. Oh, I'm sorry. I subtract. It's not going to be 90. It's going to be 6. And then I'll divide by 10. And I'll get x equals. It's basically just going to be 0.6. You'll leave it as a decimal there. So make sure I got my signs right. Yeah. All right. So moving on to the next one, number 10. One more here in the do now part, and then we'll get to the new stuff. All right. In a history class with 32 students, the ratio of girls to boys is 5-3. How many more girls are there than boys? So you're gonna have to figure out like two things here. If you put 2. Again, that's always that common wrong answer that a lot of students will just subtract. But you have to literally figure out how many boys and how many girls there are first and then subtract. This is just the ratio. This is not the actual number. So I'm going to just, you can do either the boys or the girls. It's up to you. I'm going to just go for the boys. I'm sorry, for the girls because that's first with the 5. All right, so it's going to be 5. Excuse me. Is to the total number of kids, if it was 5 girls, 5 out of 8. So I'm going to say 5 out of 8. Again, if you put 5 to 3, that's going to be messing you up because this is the girls and this is the total, or the students, we should say. And then on this side, the students is 32, and you're trying to figure out how many girls. So you'll have 8x equals 160. Then you're going to divide by 8. And you'll get x equals 20. All right, so that's how many girls there are. And then we have to figure out how many boys. So if there's 12 girls, you would subtract from the 32. So that means I'm sorry, not 12, 20 girls. So 20 girls, that means there's 12 boys. Let's up a little bit. All right, so the difference, so the question is asking you how many more girls than there are boys. So now we would just subtract. Our answer is 8. All right. All right, so hopefully that review is something you're good with. And now we're going to get to the new stuff. So the new stuff that we're going to be covering for today is going to be proving triangles are similar. We'll probably only do like 2 proofs. I would say on an upcoming quiz or so, there might be like 1 proof, or like more like a fill-in, excuse me, more like a fill in the blank kind of setup as opposed to just like complete blank proofs, just because of the nature of this. Doing like full fill-in proofs would probably be a little a little bit too much. But again, probably some more of the fill-ins, maybe like 1 like full proof for like honors or something like that. But there'll probably be more on the fill-in setup. All right, so just to review what similar figures are, here's the definition again if you needed that. And I just wanted to elaborate on some of the properties that do apply to similarity. We have these properties of congruence, the reflexive property of congruence. We have the symmetric property of congruence, symmetric property of equality, like all those things. Just want to be clear that those properties, excuse me, those properties also carry down to similar triangles or similar figures. So we do also have the reflexive property of similarity, the symmetric property of similarity, and the transitive property of similarity. So again, you should remember these. Our reflexive property of equality is that x, angle x is equal to angle x. Our reflexive property of congruence is that, excuse me, geez, angle x is congruent to angle x. It's ridiculous. Is congruent to angle x. That's our reflexive property of congruence. So now we just have a reflexive property of similarity as well. So just to note that those properties do carry down to similarity just as they did the other ones. All right, so for our properties, our methods of proving triangles congruent. The first method that we're going to look at today is AA. It's our angle, and again, just like with the congruencies earlier, we abbreviate them. So angle, triangle similarity theorem will be pretty much abbreviated AA. And basically, what this theorem says is that if two triangles have two pairs of congruent angles, then the triangles are similar. So, unlike the definition says, you need all the corresponding angles to be congruent and then all the corresponding sides to be proportional. This shortcut is telling us that as soon as we see that we have two triangles and they have two pairs of congruent angles, we can automatically conclude that they're similar. We don't need all of the sides to be written out as being proportional or all of the angles to be congruent. We can automatically make this conclusion. So what this will look like, just a quick example. Here's my little sketch here. Excuse me, for my triangle ABC. As long as we have two pairs of equal angles, that's going to be enough. Again, this is for triangles. Don't think this is for any other shape, just triangles. As long as we have two pairs of congruent angles, we automatically know they're going to be similar. And this is going to be enough to say triangle ABC is similar to triangle XYZ, and it would be by angle similarity. And that would be it. The way this will come up with the angle is the things you need to look out for our normal stuff. So what you do need to be on the lookout for, where it might not be marked, to make it a little bit more tricky, will be the vertical angles. That'll be something like before you'll always be able to infer. Another thing you should always be looking out for are the parallel lines. Because remember, if the lines are parallel, that leaves you with the alternate interior angles that are congruent. So those are the type of things that will, make it a little bit harder to spot, basically, than just the two angles being blatantly marked congruent. So that'll be kind of the way it's disguised sometimes. The second method for proving triangles similar is going to be side-side-side triangle similarity theorem. And just like the, side-side-side for congruency, we're going to say SSS, but again, it's similarity. And with the side-side-side similarity theorem, this basically says the following. If two triangles have three pairs of corresponding proportional, so that's the key word that's changing from the congruency, corresponding proportional sides, then the triangles are similar. Oops. Then the triangles are similar. So this is our side-side-side triangle similarity theorem. So what does this help us? This helps us in a shortcut, because this is just letting us know that we don't need the angles to be marked congruent, that as long as the triangles have proportional sides, I'm just going to go with something really basic for this one. As long as the triangles have proportional sides, we automatically know that they're similar. We don't need the angles to be marked congruent. So let's just go with like something basic. Like I said, we'll do 2, 3, 4, nothing crazy. And then here, let's do, we'll do times 3. So we'll do 6, 9, and 12. Excuse me. So as long as we have the sides being proportional, and again, you would always need to check that. Like, don't just assume. So you would have to do, 2 to 6, And again, you would always do small to small to check, like the smallest sides together. Then the middles would be 3 and 9. And then the bigs would be the 4 and the 12. And again, to check if they're proportional, if you forgot from the last section, what we would do there is cross multiply. So we would cross multiply here, 18, 18. This checks. 36, 36. This also checks. So we would be able to say triangle ABC is similar to triangle XYZ by side, side, side similarity. All right. And then we have one final method, which is going to, and with side, 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 it can't really get too tricky. We will do one with the like overlapping type of triangle, but for the most part, it's pretty direct. There's no real way to like disguise the side, side, side. And the last method of proving triangle similar is side, angle, side. So our side, angle, side, again, we'll abbreviate SAS when the time comes. And our side, angle, side, triangle similarity. Again, pretty much think of it just like we did our side, side, side congruence. I'm sorry, side, angle, side congruency. Only difference is that the sides are not congruent, they're proportional. So this is if two triangles have two pairs of proportional corresponding sides, and and a pair of congruent included, remember that's the key word, angles, a pair of congruent included angles, then the triangles are similar. I'm not about to say congruent. Then the triangles are similar. All right. So again, our side, angle, side similarity is a shortcut because we don't need all of the sides to be proportional. We don't need all of the angles to be marked congruent. So what it's going to look like here is just the key thing you need to remember when it comes to side, angle, side is which side, which angle is included. So if I look at this, I'm not even going to put letters here because I don't want to confuse it. If I'm looking at this shape here, I'm just going to do them in different colors. We have the yellow angle here. We have the red one here. And let's do the blue one here. Excuse me. So when it comes to these three angles, you need to be clear on which one is included, because if it's not an included angle, it's not SAS. So if it was the blue angle, that's not SAS. If it's the yellow angle, that's not SAS. Side, angle, side has to be side, angle in the middle, then the other side. So the included angle here is going to be the red one here. Angle, I didn't put a letter, but the red angle here. All right, so what a quick sketch of this will look like. Here's triangle ABC, and here's my triangle XYZ. And for this one, I'm going to say C's are congruent angle, and C and Z are a congruent angle pair. And if it's side, angle, side, excuse me, it has to be, again, the side surrounding that angle. So I'm going to just put 10 here, excuse me, 20 here, and I'm going to put 8 here and 16 here. And again, in order for this to work, you would really you can't just assume it looks like SAS, you just put SAS. You would have to, again, check the sides out. Obviously here, you can see that I picked something that'll work, but it would be, the small with the small. So you would do 8 to 16, and then you would do like 10 with the 20, and then we cross multiply, and it is going to work 160 equals 160. So as long as they're proportional, we got the equal angle, it's going to be side, angle, side. All right, so again, hopefully you took some notes on these, etc. And underneath here, I just have a couple of examples. asking you why the triangle, I'm sorry, are the triangles similar? If yes, then you would say why. So the y is going to be either your, AA, side, 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 sorry, similarity, or your side angle side. So it's going to be like which method. And then the similarity statement is going to be that triangle ABC is similar to triangle TUV, whatever the case may be. So let's start with these few examples here. I think I have about 5 or 6. And then I actually have one proof to practice with you, just to have you guys do them. So I'm going to start with example 1 with you, and then let's get started. So for this first one here, we have triangle TUS, and then we have triangle VXW. So if it's going to work, you cannot assume anything about any angle. So don't start like putting right angles here because it looks like it. Again, this is no different from before. You can't assume that anything's right, even if it looks it. So only thing we could do here as an option is to try the side method. Like there's no angles, there's no AA, so AA is out, SAS is out. The only option is to see if SSS works. So in order to try this, we would do, again, small with small. So I'm going to say the 6 with, that's the smallest side from here, the 9. 8 would be next. And then over here would be the 12. And then lastly, we would have the 10 and the 15. Now, you can just try to reduce all the fractions to check it out, see if that'll work. Or you can just go for the cross products because that's, if the cross products are equal, that's basically the way you would solidify this. Cross multiply here, we get 72. 8 times 9 is also 72. So the first one checks. And you only need to do the 2 proportions. You don't need to do like all 3 pairs. As long as these 2 work, then these 2. And then this will be 120. And 15 times 8 is also 120. So check. So this works. So the first part of the question is yes. I guess you don't have to write yes if you're going to put the method. But yes, and then it's going to be side, side, side similarity. And then the statement, excuse me, I'm going to go like small, middle, big, just so it's clear. So my small side is ST, and then, so I'm going to go STU. So I would need to line it up with small to middle to big. So I'm going to go XVW. That's important getting the statement right. So make sure you take a second and actually look at that. So that's going to be my answer for number 1. I would recommend you pause the video, try number 2 on your own, and then I'll put the answer up for that one. Okay, so for number 2, this is what I have. Your statement could be a little different because hopefully you did recognize that this is isosceles, and because these angles are congruent, you could have possibly switched up the order with E and F and A and B, but essentially that's going to be your answer here for number 2. All right, for number 3, it's a little bit harder, not to say harder, but a little, there's 3 and 4 are a little bit harder because these are the overlapping triangles. So you need to think a little differently when it comes to that. All right, so the first triangle we should be looking at, I'm going to shade it in yellow here, or outline it in yellow here, I should say, because I don't want to move the right angle. It's going to be this one. So let me do it in black and then shade it in. All right, so it's going to look like this. Right angles there. This is triangle A, L, W. And I'll shade it in yellow here as well. Pick a different yellow by mistake, but that's the way it's going to look. And then we have, because these are overlapping triangles. So then if we look at the bigger one, oh, I'm sorry, I didn't put the number. So this is 6 and this is 8. Then if we look at the bigger one, this one in red here, again, it doesn't really matter like how big the picture is. It just matters that you're labeling it right and putting the right values in. That's still a right angle. And for this is 16 and this is 12. And how do I get 16? It's because this whole side is 8 plus 8 and this whole side is 6 plus 6. All right. So now if I look at this, my options, I don't have 3 sides. So I know it can't be side, side, side. There's no way for me to get a second angle here, so I can't go for angle, angle either. So I'm going to try side, angle, side. If it's side, angle, side, again, I have to go small with, and then the big or the bigger one. So I'm going to say 6 to 12 equals 8 to 16. Again, most of us can tell that's going to work. We don't even need to bother. This is a half. This is a half. So the answer is going to be yes, SAS. So I'm going to write it over here. Side angle side similarity. And then the similarity statement, again, is key. It's going to be triangle A, I should have put law, but whatever. ALW is similar to triangle ACE. Well, we got ace out of that one, so at least that one gives me a nice word. ALW is congruent to ace. All right, so I'm going to pause the video. You guys try 4. It's of similar caliber. All right, so here's my answer for number 4. And I know a couple of you are probably not understanding where I'm getting the angle from. So let me just clarify that. For number 3, the angle is marked right. So that might have been more clear as to where we got the A in SAS. But for number 4, it's not marked. But understand that this angle is reflexive. It's shared. Like this angle K is the same as this angle K because they're both part of, like the two triangles. So let me erase this blue. So this red triangle K is the same as in the blue triangle. So even though it's not marked, it is the same angle. So that's why it's SAS. All right. The next one, number 5, is going to be our first proof here. And we haven't done any proofs in a while. So the picture's already marked a little bit with what the given has. So I'm just going to pause for a second and write my givens out. You guys do the same. We're going to stick with our, sorry, I put my pen back up. We're going to stick with our same, just standard T-table, statements, reasons. I'm just going to take a second to write them out. You do the same. All right, so I have my givens. Again, you always want to write your given. You can separate it as 3 separate steps. Put it as 1 step. It's completely up to you. All right, so now let's get started. The picture's already marked with F, G, G, H, etc. Hopefully, once you marked your diagrams or you look at the picture here, you know that these triangles are isosceles. If it has 2 congruent sides, it's an isosceles triangle. So we're going to have to write that, though, before we use the theorem. So I'm going to say triangle FGH and triangle JKL are isosceles triangles. And that's going to be definition isosceles triangle. Because isosceles triangle is a triangle with 2 or more congruent sides. So once you've established that the triangle is isosceles, you can say angle F is congruent to angle H. And that's the isosceles triangle theorem. Isosceles triangle theorem is a theorem that says base angles are congruent. If a triangle is isosceles, then base angles are congruent. And using the same, you could have written it in the same step. I'm just going to separate it. I'm also going to say that angle J is congruent to angle L. Same reason, isosceles triangle theorem. So right now we know that F is congruent to H. F is congruent to J. That was a given. So now we can say that for step 5, angle H is congruent. Because we need 2 angles, to have like a angle. Because again, if we're trying to prove them similar, we need either angle, side, or side. So I'm just trying to tell you how my thoughts and process is going. There's really no way we can figure out this other side or show that these sides are congruent. So that means kind of our SAS is out the window. I'm sorry, SSS is out the window. The next thing, if we try to do SAS, then we would have needed, side angle side. We would have had to show somehow that G and K are congruent. Could we go for that? Yeah, but it's easier to get the other ones first. So basically what I'm going for is AA. Then we would have angle H is congruent to angle J. Angle J. And that's going to be transitive property. And again, to just go through that, if F is equal to J and J is equal to L, yada, yada. Oh, I think I put the wrong letters. I'm sorry. It should be H congruent to L. Sorry. H is congruent to L, and that's going to be transitive property. And again, since F is equal to J, and then we're proving that F is equal to H and J is equal to L, then these two would end up being equal by that transitive property. That's that whole property that says, if I have the same amount of money as Tom and Tom has the same money as Jen, then me and Jen have the same amount of money. All right. So that's going to be transitive property. So then at that point, 6, we can say triangle FGH is similar to triangle JKL angle similarity theorem because we have AA. All right, I think I have one more proof here, number 6. So I'll go through that one pretty quickly with you, and that'll be it. The other ones I'll leave. Excuse me. For practice, etc. This isn't part of the proof right now, so I just want you to ignore that for the moment. We'll go through the proof, and then if I feel like it, we'll come back and answer that part. So for our proof, let's start off with our statements and our reasons. Our table, we only have a quick given, so I'll just keep the video going and write that. MP is parallel to AC. That's our only given. And our goal here is to prove that these two triangles are congruent. So the thing you need to remember is parallel. Again, parallel always is because of the angle pairs. So parallel lines, think angle pairs. So sorry for yawning. All right, so first thing, I'm just going to put numbers in here just to make this a little simpler for us. We can say that angle 1 is congruent to angle 2. So some of you will automatically do that because of the vertical angles. So let's just do that. And that'll be vertical angle theorem, which just says vertical angles are congruent. And then, again, in order to prove them similar, keep getting ready to say congruent. In order to prove them similar, our options are AA, SAS, or SSS. There's no way to get any sides here. So this is out and this is out. The only option for us is AA. So parallel lines, we also know that we get the angle pair. So let me draw these out and clarify again. So here we go. 1, 2, 3, 4, 5, 6, 7, 8. Again, the things you should remember with the parallel lines, I'm going to kind of color code them here, is that 1 and 2 would be equal. Those are those alternate exteriors. Sorry, let me not use blue. Let's try 3 and 6. Those would be congruent because of AIAs, alternate interior angles. And then we have the same side interiors, which would be like 4 and 6, and that pair is supplementary. Anyway, so with these lines here being parallel, we're going to end up with, let me just draw the transversal. Sorry, before I do that. Here's our transversal. These are alternate interior angles. So we could just say angle P and angle A. If you want to put letters in there, that's fine. I'm sorry, you want to put numbers in there, that's fine. But angle P is congruent to angle A, and that's going to be alternate interior angle theorem. And that says if parallel lines are cut by a transversal, then AIAs are congruent. So that's it. And then we have enough to say they're similar. Number 4. Because we have two angles. That's all we need. Triangle ABC, similar to triangle PBM. And it's going to be AA. All right. And then what does it say here? The reasoning. It says for the figure at the right. Oh, excuse me. Blah, 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 blah. Hold on, let me erase my nonsense here. It says for the figure at the right, suppose you were given that, could you prove the triangles are similar? So it said CA is similar to PM, and then CB in that. I would say yes, you could, and it would be an SAS situation. So again, I mean, I don't want to put exact numbers here, but they're saying like this and this are proportional, and then this side, put 2 dots, and this side are proportional. So then they're asking, would they be similar? Yes, this could also work, because even though I only marked the P and the M, these angles here are also AIAs, the angle M and the angle C. So we could do it by SAS similarity. So yes. So, but that was like an extension, yada yada. All right, so I'm done. Check out the practice problems below. Definitely try some. Again, exit card for this week will not be until next Tuesday.